Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And I'm going to discuss the ideas of rate and order of convergence. So, for example, let's start with a sequence that has this monotonous behavior. And it's more like a non-oscillatory behavior as n grows. And we saw that such sequences are suitable for Richardson acceleration, and the error model or the asymptotic behavior of the sequence as n goes to infinity is the limit plus some constant over n to the b, and b should be greater than or equal to 1, otherwise the sequence might diverge. And then if a is positive, then the error is always remains positive, so we are always above the actual limit, so the sequence approaches the limit from above. And if a is negative, and then we are approaching the limit from below. All right, so in general we can write this asymptotic behavior for our sequence as n goes to infinity, similar to a limit plus some number over n to the b plus some other number n to the b plus 1 plus some other number n to the b plus 2, etc. So n to the b is the lowest term in terms of the power or degree that defines the behavior of the error, right? That's the dominant term for the error. And we say that 1 over n to the b or a over n to the b is the leading term of the error, which is typically what is actually defining the behavior of the error. And then b is the order of convergence or the strength of convergence. Obviously, the higher the b, the larger the b, the faster the error goes to 0. And if we also discussed that when we apply a Richardson, first order Richardson acceleration, what happens is that we kind of get rid of this first leading term, and then the next term, n to the b plus 1, becomes the leading term of the error. So the order of convergence increases, which means that now the error has a faster reduction, or the error goes to 0 faster, or the new sequence goes to the same limit faster. That's why we say that the Richardson transformation actually accelerates the convergence. But then there is another idea of rate of convergence, and that gives us a fundamental thing about the behavior of the sequence. If we already know the limit of a sequence, and then we take the limit as k goes to infinity, ak plus 1 minus l, this is error for the term k plus 1, and then ak minus l, so this is the error for the kth term. All right, so error at k plus 1 divided by error at k, and that's a new sequence, so we can take its limit, and let's say this limit exists and it's a number, it's a real number mu. All right, and it's typically between 0 and 1, and the reason is that for a series to converge to the limit, we know that eventually the error must go to 0. That means that at some point for a very large k, ak plus 1, the error at k plus 1 must be less than error at k. All right, so this sequence decreases, so it converges to a number between 0 and 1. And if this number exists, this limit exists, we say that we have a linear convergence. Okay, and then if this number mu is equal to 1, we call it a sublinear convergence. So in general, mu, anything between 0 and 1, is a linear convergence. Exactly equal to 1 is sublinear convergence, and if mu turns out to be 0, which is what we really like, is called superlinear. That shows that the error of the convergence is not linear, it's actually going down by power more than 1, which means ek plus 1 over ek to, let's say, to the power of 2 or 3 or etc. That's a very much faster convergence. So linear convergence, a number between 0 and 1, sublinear exactly equal to 1, and superlinear exactly equal to 0. And one special case of sublinear, which is the worst of worst, is the logarithmic convergence, and that's when not only this limit is 1, but also when we take the ak plus 2 minus ak plus 1 over ak plus 1 minus ak. So this is the relative error, right? This is equal also to 1. That means not only the acceleration, the convergence is not fast, but also it's less fast, or it's slower than we anticipated because of how these terms behave relative to each other. Okay, so linear, sublinear, superlinear. And unfortunately, when we talk about calculus or numerical analysis, numerical differentiation and integration have sublinear convergence, and this is a problem because most of the time, using these numerical tools on sequences and series, we want to solve differential equations. And in order to do that, we have to either do numerical differentiation or numerical integration. And a sublinear convergence is a pretty slow convergence, so we have to increase n, or we have to increase the number of steps that we take. And we don't need to worry about that because we have already very powerful tools for accelerating the convergence, which is the Richardson extrapolation, because as we mentioned before, the behavior of the sequences that we end up with in numerical differentiation and integration typically follow this error behavior, 1 over n to some power, and then these are suitable for Richardson acceleration. Okay, so we said that Richardson acceleration or Richardson transformation is suited for sequences that have this kind of behavior, 1 over n to the b. And if you start with this behavior, L plus a over 1 to the n to the b, and then put it here, we see that this limit, this fraction is basically n to the b over n plus 1 to the b as n goes to infinity, which is basically 1, right? Regardless of what this a number is. Therefore, sequences with this behavior are always sublinear. And again, that's why I'm saying that the numerical differentiation and integration have sublinear convergence, because they typically follow this error model. And this error model is always sublinear. So if we have this sequence L plus a n to the b plus a1 n to the b plus 1, which is the error model, and we take the leading term here and put it in this limit, in this definition, it's always 1. So Richardson suited sequences typically have sublinear convergence. And we definitely don't like sublinear convergence because it's a very slow convergence. That's why we apply Richardson transformation. And then the problem here is that sequence accelerators do not change the rate of convergence. They only change the order of convergence. And what I mean by that is that we know that this original sequence with this error model has a sublinear convergence. And then if I apply the Richardson acceleration, let's say we get rid of this term, the limit is still a term, the same. So we end up with a new sequence that is L plus some number n to the b plus 1, etc. And the order of convergence has increased, which means the error goes to 0 faster, but the rate of convergence with this definition is still 1, so the sequence is still sublinear. Similarly, for the sequences that have an oscillatory behavior or oscillatory error model, we said that those are suitable for Aitken or Shanks transforms. And then if we put it here, we see that this error model, some number to the nth power, has a limit of magnitude absolute value of b, and in order for this sequence to converge or the error term goes to 0, b must be less than 1, all right, the magnitude of b. And this is a linear behavior, not sublinear, because b is not exactly 1, but still it's not a superlinear, it's sublinear, and we know that the smaller is the better. So the smaller the b is, we are getting closer and closer to a superlinear behavior. So this error model b to the n has a faster convergence compared to the 1 over n to the b, for example, because the rate of convergence here is b, which is less than 1. The rate of convergence here is exactly 1. All right? And this is also another reason why if a sequence is suited for Richardson, Aitken or Shanks don't really work on the acceleration for those sequences, because the rate of convergence are different here, b and 1. And even if we apply Aitken or Shanks on this oscillatory behavior, the rate of convergence remains the same. And because the rate of convergence of these two types of error models, these two types of sequences, are fundamentally incompatible, 1 versus magnitude of b, we cannot, if we apply one transform on the other one, there is no gain, because in order for these transforms to work, the rate of convergence must be compatible. All right. So here I'm just showing the Richardson and Shanks, for example, or Aitken. Richardson takes an and transforms it into bn. And if we go through with the transformation and the definition, we see that basically what happens is that bn has an error model whose leading term is n to the b plus 1 instead of n to the b. And if we take the limit or try to find the rate of convergence for bn sequence, which is the Richardson transformation of an, we end up with 1. Again, Richardson transformation does not change the rate of convergence. It changes the order of convergence. Similarly, for the Shanks or Aitken, if an is a sequence with this error model, bn is also a sequence after applying Shanks whose error model starts with b to the n plus 1. And if we take the limit, find the rate of convergence for bn, it's still absolute value magnitude of b, or absolute value of b, which is less than 1. So Shanks transform, all these transformations, they don't change the rate of convergence, they change the order of convergence. Shanks transformation does not change the rate of convergence. And that's the fundamental thing that we need to know, why these are not compatible. If I apply Richardson to an error model with this behavior, I'm not getting a good result, because Richardson is suited for sublinear sequences, and Shanks work on the oscillatory sublinear sequences. Okay. Now we can formally define the order of convergence as this limit when we take ak plus 1 minus l divided by ak minus l to some power p as k goes to infinity. If this limit exists, it's a finite number, and we just call this mu, so it's greater than or equal to 0 and less than infinity. That means that the order of convergence is p, that's the formal definition, and p is typically greater than or equal to 1. And basically the best behavior, or the ideal case, is that p is very large and mu is very small, ideally 0. Okay, so higher the larger the p and smaller the mu, we say that the sequence has a faster convergence, because the error goes to 0 faster and faster. If p is 1, which is what we have so far, and mu is 1, it's a sublinear sequence or sublinear convergence. If p is 1 but mu is between 0 and 1, it's a linear convergence. If p is 1 and mu is exactly 0, it's a superlinear convergence. If p ends up to be 2, so for p1 mu is 0, but for p2 mu is something non-zero, is not exactly 0, we call this a quadratic convergence. If p is 3, so for p1 and 2 mu turns out to be 0, but for p3 mu turns out to be something non-zero, we say that it's a cubic convergence. And you probably can guess that quadratic convergence is much better in terms of speed of convergence compared to the linear convergence, and cubic is faster than quadratic, of course. And again, because in calculus we're dealing with differentiation and integration, we are mostly dealing with linear and sublinear convergence. Now, one interesting thing that we discussed when we talked about root finding algorithms was that the Newton-Raphson iteration, root finding iterations, are in fact quadratic convergence. That's why we always say that the Newton-Raphson, or the Newton's method for finding roots, is relatively fast method or algorithm, because you can mathematically prove that it's the errors of iteration go to 0 quadratically. So they follow this pattern of e to the ak plus 1 minus l over ek minus l to the power of 2. Okay? For power of 1 it's always 0, for power of 2 it becomes non-zero, so it has a quadratic convergence. So Newton-Raphson root finding iterations is quadratic, has a quadratic convergence, which is pretty good. For example, bisection and the other method like bisection, trisection, or secant method even, they have, so bisection, trisection have linear convergence or sublinear convergence. Secant is superlinear but not quadratic. So when you write this limit for secant, p ends up to be something like 1.2, 1.5, something like that. It's not exactly 2. So here's one example. Let's say our error term is 1 over 2 to the n, therefore en plus 1 over en to the p when we take this limit. And it's something, if p is less than 1, we're definitely getting 0. If p is equal 1, we're getting 0.5, and if p greater than 1, the limit diverges, we get infinity, okay? And therefore this is a sublinear behavior, because for p equals 1, we get a non-zero number. This is sublinear. And it's linear because p equals 1, and it's sublinear because the value of the limit, this mu term, is not 1. It's something between 0 and 1. And if we have, for example, 1 over 2 to the 2 to the nth power for the error, then en plus 1 over en to the p. For p less than 2, we get 0. For p equals 2, we get 1. And for p greater than 2, we get infinity, which means which means we have a quadratic convergence, right? Quadratic means for p less than 2, this limit should be 0, which is true, so it's definitely superlinear. And then for p exactly 2, we get some number, some positive number. Doesn't matter if it's 1, less than 1, or greater than 1. It's a quadratic, so this has a faster convergence than this one. All right. Now, how to estimate order of convergence, this p term? And one practical way of estimating p is take for large k, you can construct this sequence, log of delta. Delta is the forward difference, delta of ak divided by delta of ak minus 1. All of this divided by log of ak minus 1 divided by ak minus 2. This is the delta, right? We're calculating this new sequence. This is basically a transformation on the sequence ak, right? And we're getting a new sequence, and as k goes to infinity, this ratio converges to the p. So this is one practical case. We just make k very large and see where it converges to, and that's p. How to find rate of convergence mu? The problem with the rate of convergence mu is that we don't know exactly the limit, because the original definition of mu is having the L, the actual limit. But then there are ways to look at the approximate error. So the exact error or the actual error or convergence is an minus the exact limit. But if we don't know it, we can define a new sequence, e tilde, which is an plus 1 minus an. Okay? This is basically delta an, right? This is the forward difference. And we already know that if the sequence, the original sequence goes to L, which means this en, the original error sequence, goes to 0, this approximate error also goes to 0. And you can prove that if the sequence is a superlinear, it has a superlinear convergence, then the limit of the en over en tilde is 1. That means that these two errors are equivalent to each other. So you can use this in the original definition and try to find mu. If you just search on Google for the rate of convergence and how to practically find it, you can find articles about this kind of approximations. All right. So for superlinear sequences, we can say that en is asymptotic to en tilde. That means that if we start with the forward difference sequence, it actually it's actually approaches to the original error sequence. All right. So let's go to Eclipse and try to apply this definition for the order of convergence for some of our sequences. So here in Eclipse, let's go to our sequence, and we have the sequence interface with all the methods and the transformation and the operator overloading. We have the series class that sums up the sequence. We have the Taylor expansion here that generates a sequence, a polynomial. And now let's say in the tests we try to create a new class, the test order of convergence, and we want to have a main method. And here I'm going to create a method, public static void test1, and here I'm going to invoke test1. Let's define a sequence and import it. Sequence sec1 is, for example, n goes to let's define a sequence 1 over n times 1 over n. So we're looking at 1 over n squared. Let's import this. Okay. And we know that if we create a sequence sec2, which is n goes to series dot sum over this sequence, and sequence from 1 to n, right? So we're creating a partial sum. And let's first look at the order of convergence for sequence 1. And we already know that this sequence converges to 0, so the limit is 0. And then we know that basically this sequence 1, an is 0 plus 1 over n squared. So b should be 2 here, right? This is exact. And this kind of sequence is very suitable for Richardson acceleration, for example. And the rate of convergence is an plus 1 minus 0 over an minus 0, which is n over n plus 1 to the power of 2, which is 1. So it's a sublinear convergence, which is a sublinear convergence. And let's try to find the order of convergence. So in order to find the order of convergence, what I'm going to do, I'm going to create a new sequence, let's say Pn, and n goes to what we are going to do, math.log of sec1.diff, and we're going to shift it by 1. Okay, and if you look at the shift, it shifts forward, so we want to have shift by minus 1. So this is delta an, and we can shift it, or we can basically evaluate it at n plus 1. All right, let's go back to the PowerPoint. Actually, we want to evaluate it at n minus, okay, so we want to evaluate this at n, and then divide sec1 dot diff. We want to evaluate it at n minus 1, and then divide the whole thing by math.log n minus 1 and n minus 2, right? So we take the forward difference of the sequence, the original one, an, and evaluate it at n. delta evaluated at n minus 1, and then n minus 1, and then evaluated at n minus 2. Okay, and now let's try to plot this, plot Pn. So let's call this int, or maybe long, because these are long numbers. Okay, let's call this int. Indices new int, let's say 100, and then double p-vals is new double indices dot length, and then we're going to write a for loop, int I equals 0, I less than indices dot length I plus plus. Here we're going to set indices I to I plus 1, and then p-vals I equals to pn dot evaluate at I plus 1. Okay, now the problem here is that this goes to okay, so let's start from 10, for example, and then we're going to evaluate at 10. All right, and then MATLAB chart, fig new MATLAB chart, fig dot plot indices and p-vals, fig dot actually this should be double, fig dot render plot, fig dot show. Let's add a boolean flag here, and this should be double. All right, let's see. Now I'm on Mac, so I have to go to the run configurations, VM arguments, and remove this check mark. All right, so as you can see at term 10, we are at 0.9 for Pn sequence, and we know that this sequence should converge to 1 because we already know that the rate of convergence is, the order of convergence is basically the order. So this sequence clearly converges to 1, and what we see that the rate of convergence is also 1. So this sequence can basically so in order for the rate, let's go back to the definition. So here we know that the sequence 1 over n squared is a sublinear has a sublinear convergence, right? In order for the sublinear, it means that the p must be 1 and mu is 1 too, right? So p must be 1, and the sequence that we are making, this log sequence, has to converge to 1, and that's exactly what we see here, right? So let me go to 500, for example, and let's run this. Yeah, it approaches 1 as we expect, right? And so the definition of order of convergence, and then this b here in the error model is not exactly the same. So it depends how you define this. Some people define this b as the order of convergence, but that's more like the order of error, how fast the error goes to 0. But in terms of the rate of convergence, this p here is also formally defined as the order of convergence. And what we see here is that for our 1 over n squared sequence, p goes to 1 as we expect, because that's a sublinear sequence. And the good thing here is that we can in fact accelerate p, because now pn is a sequence by itself, right? So let's say P, let's define a new sequence, Pn Richardson, and we're going to apply basically take Pn and apply a Richardson fourth order, and then P vals Richardson, new double indices dot length. Okay, and now here we are going to basically say P vals Richardson at I is Pn Richardson, evaluate at 10. So let's give the first one a color of blue and the second one a color of red. Let's also turn the markers on here. All right. As you can see, the Richardson pretty much converges super rapidly. Let me just add some titles. So X label index, and the fig Y label sequence Pn. And as you can see with the Richardson, we are pretty much there at 1 after just 10 terms. You apply your fourth order Richardson, calculate at 10, and we've discussed this before that for Richardson fourth order, as you increase the order of Richardson, there is a chance of oscillation or instability, which is very small here, but that still happens. So up to, for example, 50, 60, we don't really see this oscillation up to 40, but after that we see. But as we can see, Richardson acceleration is definitely suitable for 1 over n squared, for example, or even this log, even if this log sequence Pn, and that gives us the order of convergence based on the definition of rate of convergence. Okay, so this sequence 1 over n squared is sublinear, so we should definitely have a p equal to 1, and p is the limit of this sequence, and it's definitely 1, right? Similarly, for this sequence sec2, for the partial sum, I'm going to change it back to sec1 and maybe remove this. Yeah, we cannot do that. What I want to set sec2 here, and then define the rate of convergence, the order of convergence for that. So here we define it based on sec2. Alright, so sec2 is just summing up 1 over n squared, and we know that this converges to pi squared over 6, and then the error model, if we estimate the error by integrating from n to infinity of 1 over x squared, the error model ends up to be 1 over n. Okay, so we still have a sublinear behavior. So let's see if that actually works. So we have indices Pn now defined for sec2, which is the partial sum of sec1, and then Pn Richards. Okay, yeah, we are still getting 1. So even if we create a partial sum of 1 over n squared, we're getting 1. So that means that we are still at a linear or sublinear convergence, one of these two. And what is obvious here is that the fourth order Richardson transformation becomes unstable, and at very large n, as we expect, typically that happens. So, but as you can see, for a small index, it pretty much gives you the exact result right away. Okay, so definitely use these transformations. This also confirms that the partial sum of 1 over n squared from 1 to n has an order of convergence equals to 1, which means that it's either a linear or sublinear behavior. There is no other way. Okay. Now, if you recall, we had this sequence, let's say sig1, and we had this sequence that has an error of 1/2 to the 2 to the n, okay? And we saw that it works for p equals 2, so let's test that too. So let's create a sequence, for example, 1 plus, so n goes to 1 plus 1 over math.pav 2, actually 2 to the, so we take 2 math.pav 2 to the n. Okay, so this, our sequence has a limit of 1. The error is 1/2 to the 2 to the n, and let's call it seg2, and let's see if this sequence in fact converges to 2. Alright, we're not getting anything because I assume that let's see, 1 over, let's try 10 terms. Let's just okay, so we're plotting p sequence, and let's see, 1/2 to the 2 to the n, right? And maybe let's n minus 1, n minus 2, everything looks the same. Let's go like plus 20, for example. Let's remove this Richardson, see if we can calculate Pn correctly. No, it still doesn't give us anything. I assume that's because something becomes negative here. N minus 1 divided by, if we take the diff, n plus 1, that's definitely negative, n minus 1 over n minus 2. We can add an ABS of this and try to see if that works. No, it still doesn't work. But eventually this should give us a factor of 2. Okay, so this was the introduction, or more general discussions on the rate of convergence and the order of convergence. And then we also said that if we know the error model, we can also define order of order B for the error as well, the convergence of the error. And we said that in particular we don't like sublinear convergence or even linear convergence, but then most of the time we're just stuck with this kind of behavior because of how differentiation and integration behave. Okay, thank you for watching. I'll have more lectures coming soon, so please stay tuned, and I'll see you in the next one.